Hello everyone, in this video we are trying to follow the book Cloud-Based Remote Sensing with Google Earth Engine, Part A1 Human Applications, Chapter A1.1 Agricultural Environments. In the previous videos we tried following the other chapters and we are beginning the new section, new chapter today. There are still so many things to learn even from the previous chapters, but we want to explore further, and many things are related and also repeated. So that is the advantage of just learning the new, learning the single platform. So this chapter demonstrates us the one way to make the crop maps. To summarize, this is based on calculating the harmony coefficients and using it to predict the new values in a way very similar to the linear regression, but here the term is more different, and we say it as the harmony coefficients. So the main thing here is this equation. So we are trying to use this equation in Earth Engine for predicting the new values. The codes are all from the book's repository, and we begin by this very first line here. So this is the Tiger dataset. This dataset has the boundaries of the USA, and here in the line 13 we begin with the very common approach. We do this every time. So we are filtering the metadata, and we want to filter the specific county, that's McLean, and McLean is somewhere in the Illinois. We can understand this as the polygon or our region of interest. Then we see this region being made into the geometry. We are centering it in the map section by map.centerObject, and we are adding it as the layer by map.addLayer, and inside which we see this color as red, and the layer's name has been given. And then we see the two data sets, Landsat 7 and Landsat 8, assigned to the variable names, two variable names, Landsat 7 and Landsat 8. So both are level 2 collection 2 dataset, meaning atmospherically corrected surface reflectance data. This means any atmospheric influences in the spectral information has been removed. So there are the prior choices why one or another is chosen. So there is another called top of atmosphere as well. So it certainly depends on the methodology and the user's choice. So there are two different types of these data sets. And let's not forget that after 2022 there so everything is being on the level 2 data only. Then we have the two different functions, rename L7 and rename L8. So this function will rename the bands of either the Landsat 7 or Landsat 8. So this is done to make the names more intuitive and to make things more easier. So this is done by image.rename, and we provide the list of the new names to the image. So there are two functions, rename L7 and rename L8. We further see the two functions, add mask, and the other one is mask QA clear. So this add mask function uses the QA pixel QA-pixel bit mask into multiple masking layers, and the other function is again mask QA clear, removing all the non-clear pixels from the image. So these are important to remove any pixels which are of not of the required quality. To talk a little about this masking process, it is related with the binary values and the decimal values. So the information is stored in the bits, and the function tries to access those bits. So this is kind of complicated for me to explain, but in general, this is done just to mask the pixels that are of not the proper quality. Then we have this new function add VIs, adding the new vegetative indices. So in this case, GCVI, or green chlorophyll vegetation index, based on the provided information in the book. This has been found to be more effective in distinguishing the corn from soybeans. So here is the standard way to do it from the image.expression, and inside this .expression we have the formula, and this is followed by the selection of the bands, and we also rename the new result as the GCVI, just renaming the band. So finally we return it with the image. Then we have the start dates and end dates. So this is being done for the year 2020. Selection of the year is important to obtain the time series of the images. So these time series help in the differentiation of the crop growth stage. And the image collections are filtered with the filter bounds here. So these filter bounds will make sure that the images that we will get will be intersected with the area of our interest, that is the McLean County. And we are also filtering the image collections with the dates, so that is the start date and end dates, and the renaming has been done at the very last here. And this is being repeated for both Landsat 7 and Landsat 8. We merge the Landsat 7 and Landsat 8 collections by this function .merge, sorting it with this time property. And further we are mapping this add mask, and we are also adding the new vegetative indices to this Landsat collection. So these are all the previously written functions. So just to visualize, here we have the point inside this ee.geometry.point with two different numbers. So these are just the coordinates, and this particular point is related with the cone field, and this is the chart is prepared by UI.chart object. So this will visualize the combined Landsat GCVI time series, and we can see this in the console. We also have this CDL image. This is the crop map dataset, and the band cropland has been selected and added as the layer. So from this dataset, training and evaluations of the classifiers will be done. So let's run this all, and we see a chart in the console. So this is the GCVI around the year, and we also see the map. We see also this crop map being displayed. So this concludes the very first section. we begin the section 2, where we add the bands to Landsat images for harmonic regression. So the main objective, as told at the very beginning, is using the harmonic regression for the crop map classification. Harmonic regression is the way to extract features by fitting the sine and cosine functions. The other name of this regression is the Fourier transform, and this is pretty useful when the data patterns reappear at the regular intervals. Here in these codes, the second order harmonic regression has been fit in the time series data. So it starts with making two functions. So they add a harmonic basis and intercept. The first function here gets the acquisition time of each image as a band to the image in units of years, and from the reference date, from this reference date, the time band is computed relative to it. And there is the second function called add harmonics, and inside this function, it takes the cosine and sine of each image acquisition time and adds them as the new bands to each image. So the sine and cosine of each image acquisition time is taken and added as the new bands to each image. The main objective is to fit the second order harmonic regression. Two sine and cosine terms are added as the bands along with the constant term. A constant band is created by the division of the time band by itself, giving the value as 1. We can see this here. And then we map the add harmonics to each image in the collection. And the start date or the reference date is the January 1, 2020. And here this omega is given as 1. So this was what we had seen in the very first beginning. So this omega is the hyperparameter that controls the periodicity of the harmonic basis. We can run this, and in the image, if we see, we can see the new bands being added as the new bands being added here. Here we can see this cosine, sine, and along with other things being added as the new images, sorry, new bands in the image. So this concludes the second section, and the third section is where we fit the harmonic regression at each Landsat pixel. We can now run the linear regression using this basis as the independent variables and Landsat bands and GCVI as the dependent variables. So this is performed by ee.reducer.linear regression reducer. This reducer takes two parameters: the number of independent variables and the number of dependent variables. So when we apply this to the image collection, it expects the images in the collection to have the independent variable bands followed by the dependent variable bands. So this returns an array image whose first bands is an array of regression coefficients computed through the linear least squares, and whose second band is the regression residual. So this will be as the output. The function defined here is the array img harmonic regression. So this will help us apply the linear regression reducer to each image. We further want to have the array image with each coefficient as its own band. So we also want to rename the harmonic coefficients written by our regression to match the corresponding band. So this function image harmonic REGR or regression performs these operations. The array image is transformed into the multi-band image using the function array project and array flatten, and the coefficients for cosine, sine, and constant terms are renamed by adding the band names as a prefix. So we will see this what it does when we run this, and the third function is called the get harmonic coefficients here. This performs the harmonic regression for all dependent bands by mapping the image harmonic regression created earlier, and for function for this will be done for each band. So it creates the multi-band image consisting of the regression coefficients. And in each band we have the 5 coefficients from the regression corresponding the cosine, sine, cos 2 and sine 2 in constant terms. So in total we get 20 harmonic coefficients. After applying this get harmonic coefficients, the coefficients are clipped to the stereo area, and transformations are applied to change the coefficients to 32-bit integer, so just to reduce the memory. So we compute the fitted values by multiplying the regression coefficients with the independent variables. Then we plot the fitted values along with the original Landsat GCVI time series. We also add the serial or the crop data layer as a band to the harmonics, and we can export the final image as an asset. So this is an optional step, but this might be important for the largest stereo area, as this is the very intensive step. So we transform at the very last here. We transformed these fitted GCVI bands via division and addition by constants, just to make the nicer visualization. So if we check the console, we have the Landsat image collection with the harmonic basis. So if we check the image bands, we have the different cosine, sine as the bands. So the new thing here is this harmonics. So there are new bands. So they are the renaming was done at the second function here. So this was just making the new names for the bands, or renaming the regression coefficients. And the final image collection will have the new band here. This is the fitted, and you can see this in the chart here: Landsat GCVI time series and fitted harmonic regression values. So to summarize, this was just being done to get the new GCVI for the image collection. So this is the last section. Here the training and evaluating is done for the random forest classifier. So a random forest classifier is defined here. This is done by ee.classifier.smile random forest. providing 100 trees and a minimum leaf population of 10. Harmony coefficients is the way to provide information from the temporal dimension to the classifier. This is useful in distinguishing the crop types. So the band names can be obtained by calling the band names on the harmonic image, and the CDL band and the system index bands are removed. Then the CDL bands, or the crop data layer bands, are remapped with the cone as 1 and the soybean as the 5 and others. So this is being divided into 3 different groups: corn, soybean, and others, other crops or other land covers. And then we are getting the 100 points 100 points from the data set. So this will be used for the training. This will be used as the training sample for the model. So here we are training the model. We have our model being trained with these training points, and the confusion matrix can be computed for assessing the performance of the model, and also the accuracy can be computed as well. So as a test set, 50 new points have been used. The confusion matrix and accuracy can be computed for this as well. So the model can be applied to the entire study region and see how it works, or see the model performance across a space. The final comparison can be done with the predicted or the computed layer with the original one. So you can see where the two are equal and where they differ by calling this EQ on the two images. So white pixels will be, so we can run this first and see what we get. So the white pixel, let's wait for now. So the white pixels are the area where they agree, and the black pixels are where they disagree. And if we see here, we can see the training points and some error matrix and the test error matrix and test overall accuracy. So to summarize here, what we did was we defined the random forest classifier, provided some parameters to it. We get the harmonic coefficient band names and remove the 2 different things from them. And we also had this cropland being divided into 3 different bands or 3 different groups. So one will for the corn, other for the soybean, and remaining for the other land covers. So this was being done for the training, and then we had this 100 points or the 100 sample training points being generated from that data set, and we just applied this random forest model using those training points, and other 50 different points was also prepared to test the model. This was applied to whole study area, and after doing that we also compared the predicted layer and the crop data layer. So this is the overall attempt to summarize the chapter, and this chapter has many questions asking us to apply, try and do many things. And I hope this video was helpful to you. Maybe not that helpful, but if you have watched till the end, I would like to thank you, and I will welcome any comments. So any comments are welcomed. Thank you for watching.